Yes, sir.
So now it is not visible,
Okay.
sir.
Are you not visible? Huh? Yeah. Okay. Now.
No, now it's okay, sir.
Are you able to see the screen presentation?
Yes, sir. Yes, sir.
Okay.
Tarun, please take snapshots.
Good.
Tarun, sir,
Yes, ma'am.
but please take photographs.
Yeah. Okay. So if you're able to see the screen, okay, I think everybody is able to just see the screen. Yeah, my topic is analysis and design of RC shear walls, right? So anyway, so it's inevitable anyway. We are working an online system, so these are the problems commonly we encounter. Okay, but anyway, so we have to accept. But anyway, so again, thank the organizers for giving me the chance to present my lecture. It's basically a part of the routine design things. Of course, it's a new topic for most of the structural engineers in India, and of course elsewhere also. But I have covered the general description of shear walls, then the classification, and the design requirements and the code provisions. At the end, I'll talk about our research findings at IIT Madras in Structural Engineering Laboratory. Okay, so before we start with, so we are interested in the framed system subjected to earthquake loadings, okay, currently. Similar approach, or say maybe the same direction, one can think about the effect of blast loading or say windstorms. If you see on the screen, a typical 2D frame is considered, and it is subjected to any lateral load. When you understand, of course, you are all aware the distribution of bending moments, okay, and shear forces. So this is a typical frame subjected to lateral force. Now, actually, this is the frame. Okay, left diagram, bottommost is the bending moment diagram. Your columns will be subjected to highest bending moment at top and bottom. In between, a plastic hinge or a hinge, and in the beams also will have distribution of bending moment, that is due to uniformly distributed load, gravity load. But anyway, so one, can understand the distribution of bending moment, shear forces. And the right side, bottommost one is the shear force diagram. Actually, so the intention here is the ground motions. So we structural engineers, we construct multi-story buildings and fix it to the ground. So we have the rigid fixity connection with the ground depending upon the soil type, and the structure will move in the vertical direction, that is constructed in the vertical direction. So now actually when you see the effect of earthquake forces, because the whole mass of the building is in a rest, and when the ground motion is taking place, so suddenly there will be kind of forces, inertia forces or forces. Now this is the typical building to frame building subjected to lateral forces. So of course this is a bare frame like columns, beams, and of course the intersection of the beams and columns. And we have the slabs and other systems, right? So this is the typical one. One can understand how the deformation of the building, because you want to design a structural system, you should understand how like it is going to deform physically, and accordingly which phase is in tension, which phase is in compression, and hence. Okay, this is a typical case. I mean, the intention is something to understand the forces developed in the joint region, say. But even when the current case also, along with the frame, we are going to discuss the shear walls also. The shear walls actually intention, okay, we'll understand subsequently, is a multi-storied building. The multi-storied building constructed, say, without shear walls, say, it's only a frame system under the earthquake loads, okay, then we find there is a damage, okay, or the failure of the common point, the intersection of the beams and the columns. But of course, the loads are so high, the horizontal forces are very, very huge, and the whole structure can also collapse. Okay, this is another case where the building actually collapsed, and the critical region is a beam column. And subsequently, we discuss how the forces in the shear wall system. Now, actually, this diagram, okay, carefully observe this. It's very, very important for us to look into that. See, all the buildings existing, they were designed based on the gravity loads. That means we have the dead loads and the live loads, and assumed to act in the downward direction, and the distribution of bending moments and shear forces, okay, due to gravity loads is something different. And it is just to find all the buildings which were designed based on gravity load design approach. It's fine, beams normally stronger, columns okay, as per the moments the shear force acting. Now, actually, now the scenario, now the trend is changed. The loads are changing now. All the buildings constructed according to the gravity load system now, they need to face the changes in the loads. That means the ground motions or windstorms, okay, or maybe blast loading. So due to this change in the loading system, now actually the existing system, which was designed for gravity loads, you may experience, like say, the points here, the dark points here, okay, when the earthquake moments are acting, earthquake forces are acting, so you experience the critical region between the beams and the columns, it's a joint, will experience plastic hinge. The plastic hinges will be formed at the junctions of the beams and the columns. So that is very, very important, okay, issue separately, okay, we can deal with. But now that is just for understanding. Now, we cannot allow the plastic hinges to form in the joint region. Otherwise, as you observed in the previous diagrams or even the current diagram, the plastic hinges form in the joint region, they will lead to collapse of the structure as a whole. So therefore, we don't allow those things. We don't want that to happen. So therefore, it is important for the structural engineers to analyze the building. We have to analyze the system, we have to calculate the bending moment shear forces and the existing building, the existing element, you know the reinforcement details, know the sectional dimensions, know the materials, and calculate their capacities, either bending moment or shear strength or flexural strength. And you compare with the forces acting, bending moment acting, shear force acting, or any other force acting. That's how we do. See, any building, we can model this one in computer and assign the loads, okay, design loads, including now earthquake loads. Say. You calculate the forces and the shear forces, bending moment shear forces developed every location along the beam length, along the column height, at the junction of the beams and column. So we will understand what are the loads you assign, design loads now, and what is happening in the real structure. Analyze that, you see whether the structural system is safe against the earthquake loads. If the system is not safe, then actually you need to think about something. Now actually when you think about, because as a whole, because it's already constructed, you cannot do anything inside because, and otherwise you disturb everything. Whether you can do externally, that means think about a kind of system which will bear the horizontal forces coming from the earthquake. That means the shear wall one way. Okay, so that we'll just discuss later. Then this is the another one here, the column sway. Here is a joint failure. It's not acceptable. And when you take the bottommost storage of the building and you analyze, you find some of the columns will fail due to formation of plastic hinges in the columns. That is also very dangerous. That is also very dangerous because lateral forces are acting. A small force is good enough to collapse the whole system. So therefore, this is that. So therefore, you have to analyze the building and we have to assess the capacity and you have to compare with the forces acting, and then you think about what needs to be done. Okay, that is anyway. So something you will come retrofitting globally or locally. Locally, maybe not possible because already existing and it's inbuilt, but maybe globally you can think about. Global way, either you can provide parallelly, like a bracing system using steel, or yeah, adding some shear walls externally and joining the whole system so that all the loads, okay, that is horizontal loads, can be borne by the shear walls. Now actually, once you have a model, your model building model, and you know the loads acting, you know the span, okay, and you have assigned the properties of the material, sectional dimensions, say, you analyze the system. When you analyze the system and you select the dimensions so that the beam should be weaker compared to the columns, so that when the lateral forces are acting, the column system will be very strong, no weakness in the column, no weakness in the joints. Otherwise, if you see the first one here, column shear failure, joint shear failure, and here sway failure, column sway. So to avoid these two types of failures, which are very, very brittle. There's a brittle failure, it's a collapse kind of failure, and we don't want that kind of thing. So any system existing, you need to assess the capacities, and if the capacities are not adequate to withstand the forces coming from the design load, then you have to think about. But now, otherwise, if it is a new building, you want to propose, say, construction design. So we have to analyze the building properly, assigning the current design load. When you do that, you see that the capacity of the beams should be lesser than the capacity of the column. So if that is the case, you are designing. Once you get the moment shear forces from the analysis, then you assign the dimensions, you provide the reinforcement so that always in the refined structural analysis design, the beam should be weaker than the columns. That is the case. Beams, if at all, plastic hinges will form in the beams locally. There is a formation of plastic hinge. Formation means yielding of the reinforcement in the beam. That is allowed so that you will have sufficient warning. Therefore, plastic hinges, or the capacity of the beams can be accomplished or achieved before the capacity of the columns are joined. So that your design will become more ductile kind of thing, more local failure in the beam, and no failure in the vertical system. No failure in the joint, no failure in the column. So that's what actually we have to do. So therefore, while designing, when you're talking about earthquake load system, earthquake loading, we have to design the building so that the building as a whole should have sufficient, ductility, the ability to withstand the forces, so that the local failures can be allowed in the beams only, nowhere in the columns or joints. So that's what actually is very important for you. So simple. So therefore, while analyzing, while assigning the sectional properties of the joining member, the designer has to be very careful, and the reinforcement, what you provide, that also matters. So therefore, this gives you the design approach for the structural system, against the lateral forces from the earthquake forces. The same is the case in case of blast, other loading effects also. Now actually, so that is just background. Now you can design the system only beams and columns of a joint. It's a frame system. You can also combine the walls, because it is the force which is destabilizing the whole building. The destabilizing effect can be counteracted by providing lateral resisting system. Either you can design very strong columns, more number of columns appropriately located, or along with the column, you can also think about providing wall kind of element, wall elements, okay, depending upon the, okay, the planning of the columns and other things, okay, I mean requirement. Now, actually, if you see the building construction, so we have the load bearing type. When the loads are only gravity and they induce compressive stresses in the wall. So whatever the conventional way of construction, okay, using your building material so that loads will induce only compressive stresses and all your load bearing structures, they come under this category. So always we find the compression. To take care of the compression, the loads can be borne by the columns, okay, or maybe walls, okay. And we don't design the, okay, walls for tension. That means we see that the loads will be type gravity type and always the compression, and there is no issue at all. It's a simple load bearing type. But when actually the wall has to withstand some other forces which will destabilize the building, that means you experience a kind of tensile stresses due to bending moments acting in the wall. Therefore, in such cases, wall has to be designed with reinforcement, either as a masonry building, masonry wall, or concrete plain wall. But the gravity loads are only inducing compression, it's fine. But when the loads are, okay, laterally acting, lateral forces will try to deflect the vertical member. There, tension is likely to be developed in the system. There, as you understand, the wall should be provided with reinforcement in the weak tension regions. So there actually reinforced concrete will come. Okay, but then actually to resist the lateral forces, it's already proven that, okay, in the plane of the shear wall, the plane of the wall, okay. So RC walls are specially designed in the building to withstand the lateral forces. For gravity loads, no issue, okay, but only when the lateral forces are acting due to the wind loads and earthquake loads or impact or other blast forces. So we have to calculate the bending moments acting, which phase is in tension and which phase is in compression. When the reversal of forces are taking place, then hence you need to think about the appropriate reinforcement. So actually, so now it is a wall, structural wall, but now the shear wall. Shear wall is mainly designed for withstanding the lateral forces in the plane of the wall. Definitely, loads will be acting, lateral forces will be acting in the plane of the wall. And this wall is a very important element in the whole structural system for withstanding the lateral forces, because the lateral forces, okay, when you calculate on a horizontal plane, it's a huge force acting which induces horizontal stress, that is the shearing stress we define, okay, due to wind forces and earthquake forces. So therefore, a huge shear force is acting. The elements which will resist the huge shear forces are all the structural wall. So they are called shear resisting walls, shear walls. Okay, so therefore the shear wall came in that way. The walls which will resist the lateral forces from the wind effects, earthquake forces, or blast load. So we say, but again, the same shear wall can be coined with like the structural wall. Most of the international codes, they just simply define reinforced concrete wall or structural wall. Okay. Now, actually, you can understand. So, what is the what are the different components? This is the typical building. So, this is the whole building. So, we start with like say combined footing or isolated footing. Okay, then we have the columns, beams, and slab. We have the columns, we have the beams, and we have the slabs. It is a frame system. But in between, along with the columns, beams, and slab, we will also have a structural wall. Say again, this is the structural wall. The structural wall has to be again connected to the ground. We should have a very stiff element foundation here. Okay, RC shear wall. Okay, this is the foundation. So that is actually, so this should be in the vertical direction. The whole purpose is if the building is pushed to one direction, the wall should withstand the pushing action. So therefore, the walls in the building are meant for withstanding any horizontal force coming from the forces of wind, earthquake, and blast. Now, actually, the shear wall is okay. Sometimes why it is called shear wall? Because even bending moments are very significant. The flexural failures are predominant, but still it is called shear wall because basically the wall is going to resist all the horizontal forces or maybe partly. So therefore, it is inevitable for the designer when the height of the building is so high, or say tall building, it is inevitable to have a kind of wall which is called shear wall. Okay, so in the case of particularly earthquake, okay, of earthquakes of large intensity, or say windstorms. The windstorms like the 270, 300 kilometers per hour, okay, or earthquake force like in zone 4 or zone 5, it's very huge force. Maybe ordinary column system, it may be expensive. Therefore, in such cases, okay, so to take care of the inertia force and to take care of the gravity load, then the shear walls will have an important role. Okay, so therefore, normally, initially, when we were not aware of the earthquake forces, the vertical walls are accommodated in the building to take care of the wind forces, basically. Okay, maybe in India, the wind force may not be very high, except like sea coast. Okay, but otherwise, the forces some elsewhere, like when we have windstorm, they're very huge, they twist the whole building. So for seismic forces, special design considerations for safety requirements. So therefore, windstorms, these are normal ones, but when you're talking about high intensity earthquake, so the wall should be of a special, so specially designed. The shear walls for withstanding wind or earthquake forces are generally of concrete or say masonry. But a masonry is weak in tension, okay, then there's a possibility of cracking, but reinforced concrete. So as per the requirement, you can design the member dimension. You can also accommodate the reinforcement as per the requirements. Then actually, where do you place them? You place everywhere or just as you like. You cannot place the shear walls wherever you want because we have to look into the serviceable condition. Okay, some components are okay for accommodate for serviceability. Walls provided normally the shear walls can be accommodated between the columns. Columns and shear walls can act together. Then we have the staircases, and to support the staircases and also to utilize the space properly. So the stair, okay, walls, the walls can be accommodated. And again, we have the lift. The lift again, you need to provide the columns and say some other system. 1 second. Okay, so now actually walls are provided between wall columns, stair wells, lift wells, toilets, or utility shop. I tell you after 2 hours. Okay, so utility shops. Okay, then that means okay, you understand the building, you plan the building, you know the functional requirements of each room, each component, and you know the other we have columns, stairwells, lift wells, toilets, whatever. So to properly, okay, effectively utilizing the service components, so we can think about the location of the shear walls. Then the important um, area in which the shear walls are inevitable. Like we understand the flat slab system, we have only slab, and that will transfer the loads directly to the columns. Okay, and no beams, no beams. So ribs will be provided in and around the columns. So as per the shear force requirement. So the flat wall, tall buildings like with the flat slab system, they are highly vulnerable for earthquake forces. We don't have any diaphragm action. We don't have any resistance from the flat slab system. So there you want to have, more clearance, horizontal or vertical, and say without being only slabs and column. There actually conveniently the shear walls are accommodated, okay, and there it is very, very important for you to design the flat slab system with shear walls, okay, because the flat slab system we don't have any resistance against the lateral forces. Okay, then anyway, as we understand, the shear walls or the walls are actually meant for wind forces only. But now, wherever you go, you will find the shear wall only for earthquake forces. When you say earthquake forces, it is a special design requirement. Anyway, but initially again in a tall building, so concrete was not very popular. Masonry was not so popular, but the steel system, because the industrial development, steel elements of different sections were available. And so as bracing elements, you can join the main system to secondary system. So it was very easy for the fabricator to complete the work very fast. Okay, but actually now that is gone. But now in all your tall buildings, only reinforced concrete shear walls are okay predominant because it's versatile nature. Now, actually, so we understand how the shear wants to be located and what exactly happens, how the loads will be acting. For example, see here, this is the typical building plan. It's a building. So there are some columns in between, and this is the boundary, that is outer wall, outer wall, outer wall. So here, now, this is a plan. This is the longitudinal direction of the building. This is the shorter direction, longer direction. So now,
Sir, sorry to interrupt you, sir. Sir, your voice is not audible, sir. Sir, sorry, sir. Your voice is not at all audible.
Sir, you are not audible, sir. Hello, sir. Hello, sir. Hello, sir. Hello, Miss.
Ma'am,
Hello.
ma'am,
Sir. Is sir audible okay now? Audible? Tarun?
ma'am, your voice is audible, ma'am, but sir's voice is not audible, ma'am.
Is okay now?
Sir, now it is okay, sir.
Hello?
Sir, now it is okay, sir. Now it is okay.
Okay. Now it's clear?
Yes, sir.
Yeah,
Yes, sir.
okay, fine then. Yeah, okay. I think it's something wrong. Okay. Okay, so this is the like alignment of the shear walls. Um, we can have the shear walls A and B. They will take care of they will take care of the forces acting on the larger projected area, and shear wall C and D. So they are aligned this way because to take care of these forces. So therefore, the whole idea here is when these forces are acting, this is the plane of the shear wall along this line, and there is a plane of the shear wall. So the load should be acting in the plane of the shear wall, and it will deflect. Shear wall will deflect. Shear wall will deflect, and we have the tension and compression develop in the wall. So when the force is acting in this direction, then we'll have the shear wall C and D. Okay. Okay. Now, if you see the, briefly, the forces actually that are developed. Shear walls are subjected to. So there is a variation of shear force along the height of the shear wall, which is maximum at the base, and a bending moment, again, it maximum at the base. So we can calculate the bending moment at the base, and of course, different story levels. And the load from the building above, that is a gravity load, will also act. So therefore, we have the lateral shear force, we have the bending moment, which are acting in the plane of the shear wall, and also gravity loads will also add, okay, some loads, compression loads. Okay. Okay, this is something like, so for understanding more, the shear walls are critical depending upon the height of the wall to the length of the wall ratio. It's called aspect ratio. Aspect ratio is the ratio of the height of the wall to the length of the wall. So typically, so when the high-rise shear walls are adopted, they will be subjected to very high bending moment, and reinforcement, okay, has to be designed for taking those forces. So typical shear wall, we can see HW is the height, LW is the length, and thickness is the H. Okay, this is the typical wall. This is the typical wall actually. So subjected to force like this. This is this one. This is the plane of the shear wall here. This is the alignment of the shear wall. Okay, thickness of the wall is H, length of the wall is LW, and the height of the wall is, okay, HW or H whatever. So now the ratio of H to, okay, LW, that is the aspect ratio. The shear walls are classified according to the aspect ratio as a stout walls or squat wall, okay, or slender walls. Okay. Now, so this is the typical reinforcement, okay, to be provided in the shear walls. So the reinforcement is nominal in between over a distance, okay, within, okay, say maybe 0.7 or 0.8 times the length of the wall, and the end region will be specially designed with the reinforcement so that the moment capacity can be increased by considering end region with special reinforcement, and small d is the effective depth of the wall. So therefore, SV is the spacing in the vertical direction, and SW is the spacing in the horizontal direction, because the walls will be subjected to gravity loads, horizontal forces, bending moment. Therefore, we have to provide the reinforcement in the two directions. And not only that, the reinforcement has to be distributed in two curtains on two faces, so that this is the detailing typical. With excellent performance of buildings with the shear walls, even under seismic loading, the earthquake resistant design. In earthquake resistant design, actually the whole idea is to control the loss of, okay, human life and also property. We don't let the building collapse. So we have to think about, we have to design the system for earthquake resistant, okay, load. Now, actually, it's good detailing. The difference between normal walls and the shear walls adopted in the earthquake resistant design. The shear walls to be adopted in earthquake resistant regions, earthquake resistant design, okay, they have to be properly detailed. Most important property of the shear walls in the seismic design, okay, is a good detailing, because the loads will be reversible and we have the repetition of loading, and to take care of all those things, tension becomes compression, compression becomes tension. So we have to provide, okay, sufficient reinforcement and also proper detailing. So the detailing will add to the ductility. Then again, important thing is the position of the shear walls, okay, in the building. The shear walls provided, it should not lead to secondary effects like attraction of torsional forces. When you have the tall building, when the shear walls are symmetrically planned, and the shear walls will be very efficient in withstanding gravity loads and lateral forces. But if you have not planned the building properly or symmetrically, then definitely there will be the concentration of mass, concentration of whatever, so other thing, okay, then it will lead to some eccentricity, and that will cause torsional moment when the individual columns are individual columns are considered, then there will be torsional moments in the columns and shear walls. Okay, now actually very briefly the classification of the shear walls. Okay, so conveniently IS 13920 classifies the shear walls like simple rectangular type. It's a plain wall, and the plain walls provide the special reinforcement. The ends are maybe a kind of enlargement of the thickness. That is a flanged walls or say ribbed walls, whatever, bell type wall. Okay, and conveniently again to share the load among like 2 or 3 shear wall, so they can be joined by beams called coupled beams, so coupled shear wall. And we have the rigid frame shear walls also, rigid frames combined with shear wall composite action. And we have the frame system in between infield wall. Then again, due to some architectural reason, the shear walls can also be provided above like in a column system. So column supported shear wall. And then whenever we have the core, so core type shear walls can be. Now actually these are geometrically, so we can see the shear walls like that. These are all the shear wall. This is the plain one. This is the one which is provided with say end stiffeners, or special reinforcement. These are the shear walls connected with the beams in this way. And this is like a frame system on infield wall, and this is the column supported shear wall, and this is a core shear wall. Actually, so simple rectangular wall, if you consider, then actually bending moments and shear forces from the analysis. Okay, they act in the plane of the shear wall. Okay, so in the plane of the shear wall, horizontal forces, the vertical forces will act in the plane of the shear wall, and the lateral forces will try to topple the wall. But there actually the reinforcement can be distributed uniformly along the length of the shear wall, or the reinforcement can be like a normal distribution in the middle regions of the wall, or especially reinforcement can be concentrated in the end regions. So therefore, code says that the shear walls, like the plain walls, provided with the uniform distribution of reinforcement, not effective compared to the same shear wall provided with a nominal reinforcement in the middle region with some concentration of reinforcement in the end region. So between 0.7 to 0.8 of the total length in the middle region, we provide nominal reinforcement within like 0.15 times or 0.12 times that of the length in the end regions of the wall. If you can accommodate reinforcement in the end regions, so they will act as like a special vertical element combined or integrally acting with the nominal wall. So that is more effective than the wall provided with nominal distribution. Then actually here what happened, the end regions of the plain wall can be enlarged. That means a flange can be developed, created, or say the thickness can be increased so that additional head or bulb can be created. Or in the plain wall itself, the reinforcement concentrated in the end regions will have more stiffness compared to the elsewhere. So therefore, this type of arrangement of reinforcement are increasing the dimensions at the end regions, are providing special reinforcement. That means you are increasing the stiffness by increasing the concrete area, or by providing the steel reinforcement additional, the end way you are increasing the stiffness. But these walls are very effective, when compared to the plain walls, because the advantage of having end regions, they have more moment capacity compared to the plain walls. So therefore, but when you increase the stiffness, then these end regions will attract huge earthquake forces, and they dissipate huge amount of energy, and the failures are likely to be in these regions. So therefore, subsequently, when the system to be repaired, it looks very expensive. So therefore, in such cases, another type of shear wall is, so two shear walls can be combined by, coupled beams. Actually, when two shear walls are combined together, then these beams connecting the two shear walls will increase the integrity and also the lateral resistance of the whole system. So carrying capacity will be significantly improved. But the idea here is, in the coupled walls, the shear walls are intact, they will not fail, but the beams provided with, a special design reinforcement, they will have very high energy absorbing capacity. Plastic hinges should be fall in those beams only, not in the shear wall, and they are like energy absorbing element. They may have double curvature also, curvature changes. So therefore, these beams are called coupled beams. So they are nothing but a very high energy absorbing agents. So now the design of the beam should be such that, so they have to be designed with proper detailing, proper like capacity also, but they are weakly designed, compared to the shear wall. Shear walls, though they take the lateral forces, but beams will experience plastic hinges in the beam itself, nowhere else in the shear wall. So therefore, the coupled shear walls are very effective in withstanding the lateral forces. So of course, this is something like calculation of the force acting in the beams and the number of plastic hinges from the shear walls and the coupled beam. The design of coupled beam is very important. The design of the coupled beam. So this is the coupled beam. This is the shear wall. This is another shear wall. These two shear walls will be combined. Now this coupled beam should be designed properly. Actually, the diagonal forces are likely to be acting. So there is a diagonal reinforcement has to be designed. So a strip of reinforcement along this diagonal, strip of reinforcement along this diagonal, and also the distribution reinforcement in the beam itself. That is another thing, is a rigid frame system, the frame and shear walls. Anyway, so there actually the interaction of the frame system and the wall. So when the frame is deflecting, then the wall will take care of the shear. That's vice versa. So that combination of the shear wall and the frame will have the interaction. So this is something interaction diagram. The moment without frame, very much less, and here the with frame. So this is something. So there is a kind of reduction in the moment or action of shear forces in the system. But anyway, so we have to understand the composite action of the rigid frames and the shear walls combined. Then anyway, framed walls, infill. So it's anyway, whatever the infill walls you add in the system, they may take a little more load, but other than that, then compared to the ductile and all, they may not contribute. But due to some architectural reason, the ground floor system may be with columns only, but when you move in the upward direction, you may have the shear walls. But otherwise, some cases you will find the floating columns. So we don't find the columns in the ground level, but you can find the columns in the upper floor. Due to some expansion of the system. Then the core type. In buildings, so elevators, then other service areas, so we can have the core, and core will be acting as a shear wall. Now actually the shear walls can also be classified according to the function behavior. So now actually the shear to shear, the shear is very high predominant, and in this case likely the height to length of the wall is maybe small, but in such cases shear is going to be predominantly acting in the wall. So they are classified as shear walls, shear predominant wall. Then the deflection, lateral deflection is very small, but the strength is very high. So these are actually slat walls, stout wall. Then another one is ordinary moment, shear walls. So the deflections are very huge, and they of course strength wise, but the capacity, the design is controlled by the flexural moments, because they are the height to the length ratio more than 2. They are classified as slender wall. The slender walls predominantly fail in flexure. So therefore, the wind loads and earthquake loads or whatever other lateral forces will destabilize the system due to bending moment. But in the first case, the problem is due to the high shear. So therefore, the shear critical shear wall, flexural critical shear walls, depending upon the height to length ratio. Then actually the special walls meant for seismic regions with good detailing to dissipate significant the amount of energy under the seismic forces and say cyclic forces. Okay, I think they're given me so 11:20, maybe in 5 minutes I'll just quickly finish. Okay, so now actually one can go through the guidelines given by the court. So now actually the design of walls, because some dimensions we can like a thumb rule we can have it in mind. The wall thickness should be at least 150 mm. Remind. So either zone 3, zone 4 or zone 5, the thickness of the wall should be minimum 150. Just okay, due to some reasons you may deviate as per the code, it's a failure. It should not be used. Okay, then actually when you want to use the flanged wall, the effective flange width, that is lateral direction normal to the direction of the wall. So this actually, when two adjacent walls will have very closely space, then actually the flanges should not be, the flanges should not again overlap. There, the effective flange width used in the design of flange wall shall be extended beyond the face of a distance. That is something, half of the distance between the shear wall. Okay, there's a web, two webs you will have. Between the two webs, we will have the distance. The extension of the flange should be half of the whatever the clear spacing, or 1/10 of the total height of the wall. And shear walls shall be provided the reinforcement in both land transfer. So it's important. It's very, very important. The wall has to be designed with reinforcement in the horizontal and vertical direction. That's a typical reinforcement detailing as shown. And the minimum reinforcement, okay, in any direction is 0.0025 or 0.25%, and which is distributed uniformly across the cross section. It's very important. Okay, so thickness is okay, thumb rule, and the reinforcement minimum is 0.25% we have to provide. If the factor shear stress exceeds 0.25 FCK and the thickness exceeding 200 mm, then actually the reinforce shall be provided in two contents. It's important. So whether two layers or one layer. So if you provide one layer, say center slip, what will happen to the lateral force acting on that? Okay, then if you provide two layers, each layer on each face, and come tied together, we'll have more capacity even under the vertical loads, or even there's a moment also. So therefore, two layer, okay, and in each layer, okay, then we should have the reinforcement properly spaced. The diameter of the bar to be used 1/10 of the thickness of the wall, and the maximum spacing of the reinforcement. These are the details. So the length of the wall by 5 or 3 times the thickness, or 450 mm, whichever is less, smallest one. LW is the horizontal length of the wall, TW is the thickness of the wall. And now the shear force, so anyway we have to calculate. You know the dimensions of the shear wall, you know the forces acting, calculate the shear force, VU by TW, DW. Okay, then actually this is similar to your beam shear. But here DW is effective depth of the beam, the effective depth of the wall. Because we have the length of the wall, that will be the depth of the wall. Okay, now here use IS 456 for calculating the shear capacity in table 19. Okay, and calculate tau v and calculate the capacity. If the capacity exceeds the stress, then you don't have to provide any reinforcement, but we provide the minimum reinforcement. If the force causing shear stress exceeds the capacity, then you need to provide a form of reinforcement. What you calculate in the case of a shear reinforcement like vertical stirrup, the similar equation we have to use, but here the designations are different. AH and DW, horizontal shear reinforcement, and DW is the effective depth of the wall. Actually, the spacing of the reinforcement in the vertical direction. And so the reinforcement to be provided and the shear force to be resisted with shear reinforcement is the shear force from the calculation minus the capacity of the wall. So that is the remaining amount of reinforcement we have to distribute in the horizontal direction. And the amount of horizontal reinforcement should not be less than the minimum 0.25%. And the vertical reinforcement should not be less than the horizontal reinforcement. These are some of the guidelines for you to design the shear wall. But anyway, from your analysis, you will know what is the bending moment, what is shear force. But these are the core provisions one has to follow. Similarly, you calculate the flexural capacity, okay, and we have the columns, we have the shear wall, total moment, distribute according to the stiffness value, and assign the values for the shear wall and design for flexion. Okay, so then I also, when you have the end regions like a columns and shear walls and column, then what is the amount of shear force or bending moment to be shear? So anyway, in walls without boundary elements, vertical reinforcement shall be concentrated at the ends of the walls. So the ends of the walls will provide special reinforcement like 4 numbers or 12 mm tied together. They will act as special reinforcement column. The columns will attract a very high bending moment from the center of the wall. Okay, when you take the center of gravity of the columns on either end, and these two will act as a tensile member, and they have very high bending moment capacity. Okay, now actually the boundary elements are the elements, special elements added to the shear wall to increase the stiffness and also lateral carrying capacity. So therefore, either you can increase the thickness or you can provide additional reinforcement. Either way, then these end members or the boundary element will have very high capacity of the shear wall. So the loads to be designed, okay, loads for the design of the boundary element. So one can calculate the moment acting from the load and the moment from the shear wall divided by the center of gravity of the wall or center of gravity of the boundary element will have the force that is acting in the boundary element. And hence, once you know the amount of force to be acting on the boundary element, and you can design the boundary element. So the flexural strength of the boundary elements also, okay, so you can, like the boundary elements can be designed as column elements, columns, and columns, okay, you know the detailing. So minimum area of cross section of steel is 0.8%, maximum is 6%. But when you look into the practical conditions, the condition of reinforcement, so therefore 4% you use as column. So they are basically like columns, but interaction of these boundary elements with the shear wall is very important. Separating the contribution of boundary elements and the shear wall is very important. But IS 13920 has given an expression for calculating different components of the bending moments or shear forces, whatever in each component. You identify, idealize, and calculate individually and design them as individual elements. But anyway, now again the coupled wall. So coupled walls, actually shear walls can be designed, but actually the design of the coupled beam is very, very important. Coupled beam is like an energy absorber. Then actually code has given at least 4 bars of 8 mm diameter shall be provided along the diagonal. I have shown 2 diagonal bands. In each diagonal band, so 4 numbers of 8 mm diameter. And also, of course, there is a distribution reinforcement, proper tying of these things, at least 100 mm spacing of the ties in the beam, so that they will be like plastic hinges form, and they have to deflect, they have to absorb more energy. Okay, so therefore, and properly they should be anchored into the shear wall. Anchorage is very important. Distribution of reinforcement is important, and maintaining the position of the diagonal bars very, very important, so that they will absorb very high amount of energy before failure of the shear walls. So therefore, shear walls will not fail, but beams will fail. But before failing, they undergo plastification. Huge amount of energy will be absorbed by the beam, and hence they are very safe and effective. And anyway, any reinforcement bar, you should have proper anchorage, so that when the forces are acting, say tension, they should not be pulled out of the concrete. So therefore, then again the tying, again splicing. You should not have normally splicing, but even splicing can be done only 30%. In the critical regions of bending moments or shear forces, no tying, no splicing. Even if at all splicing is occurred, the splicing has to be done only 30% of the part. But anyway, wherever we have lacking of the or splicing of the splicing region has to be provided with proper confinement reinforcement, so that bar should not be pulled out of concrete. Now actually when you understand 13920 like that, there are many other codes available internationally. So they have mentioned 2 layers or 1 layer or thickness, whatever. This table gives you the complete description of the code provisions for the design of shear wall. And of course, this is for the boundary element, the thickness of the boundary element and the design of the boundary element. So one can think about it. Okay. Now, yeah. Okay. So, I mean, if you give me 5 minutes, okay, very quickly. So now actually that is the general part. It is how to analyze and design the shear walls. But now research part. So we identified square shear wall with a different H2 length ratios 1.0, 1.25, and 1.5. We like to understand how their behavior, strength, stiffness, then the ductility, okay, by conducting, okay, testing the shear walls, huge shear walls in the lab. Bottom one is provided to be fixed to the strong floor, and we have cyclic loading and monotonic loading. And this is the web part with the flange, and this is the top beam adapted for applying the lateral force. So this is the setup here. We have this base here fixed to the strong floor. This is the shear wall and provided with again top beam. Top beam is provided with actuator to apply the load lateral force. So lateral force are applied here and fixed at the bottom. There is a real wall in the lab. So we found this is the typical loading history. So we have to apply the displacement control. And actually, so we applied different displacement amplitude, and we understood what is the load versus deflection response, and a lot of information to be gathered. So many LVDTs were connected, and a lot of strain gauges were used to gather the data. Okay, now here stress and energy absorption, stiffness, degradation, and this is the failure pattern. This is okay, it's under the seismic loading, it's a cyclic loading. We find like net kind of thing. Or at the bottom, the shear walls fail, okay, due to shear, very high shear. So here, this is the kind of setup. Okay, we have the crack pattern and load versus deflection response. Okay, that is needed for us to calculate the energy absorbed and also the activity. So for different walls with the aspect ratio 1.0, 1.2, and 1.5, we found what is the effect of the height of the wall. That is the aspect ratio. So here displacement ductility. So displacement ductility is high in smaller size compared to the larger size. We have the actual load versus deflection response. We have the idealized load versus deflection response. Okay, now is a cyclic of the first hysteresis loops created. This is for the shear wall version of there is a shear wall after earthquake loading and a comparison. So actually the stiffness has come down after testing even the refined shear wall, though the capacity looks good, but actually the stiffness has come down significantly. So these are the stiffness degradation curves with a normal and normalized. Okay, so stiffness degradation indicates the ability of the shear wall, and this is actually cumulative energy. The energy absorption in the walls. Okay, small size walls they have more energy absorption capacity compared to that. As the volume of concrete in the shear walls increases and the shear loading, energy absorption looks high in the case of smaller volume of concrete compared to the larger volume due to like some kind of Weiber's weakling theory or some kind of probability of formation of voids in concrete. Okay, so this is actually my presentation. Okay, so thank you for your patience. Okay, and thanks the organizers for giving me chance. Okay, again I apologize for the technical problem, but anyway it's fine. Okay, thank you. If you have any questions, yes. I'm done.
So thank you for your lecture, sir. Participants, if you have any queries, you can unmute yourself and ask the questions. Participants, anyone please, if you have any queries.
Sir, good morning, sir.
Yeah, good morning.
Sir, can you show once again page number 42 and 43, sir?
Page number 40.
2.43.
What is that?
That's a table, sir. There is
2
a
and
table.
43.
Yes, yes.
Tell me, what do you want from that?
Code recommendation, sir.
Yeah, tell me.
I need
Tell me,
screenshot
what
of
is
that.
that? What is your question?
I don't have any question, but I need screenshot of that, sir. Just I need screenshot.
Oh, you want? No, this information will be given. Otherwise, I'll send the PPT to people. Okay, that you can take. Okay, if you have any question, clarification, I'll do it. But for taking photos, it's okay. Anyway, that recording, it's okay. That will be sent to all the participants, I think. Okay.
Okay, sir.
Yeah. No, these are all like compiling the code provisions available. It's only you want to design the code, design the shear walls as per IS or the other codes, it's okay. I mean, you can find anywhere, but of course, this only is a complete compilation of this. Okay. Yeah. Anyway, they are actually recording that. Everything will be there, and you will be given this. Okay. Yeah, information. Yeah. You are interested in number 2 and 41.
42 and 43, sir.
Now you take it's 42 unable to see.
Yes, sir. Sir.
Hello? Yeah, okay.
Sir, next
So now you can
page. Sir.
take photo. I think this go-to meeting, I think this is not very supportive. I think there's a lot of problems. Yeah. Okay. This is the 42 is for the shear walls, 43 is for the boundary elements. Okay. This is related to boundary element. What is the horizontal reinforcement? What is the vertical? Yeah. 43 is for boundary element, 43 is for the shear wall. Okay.
Okay, sir. Thank you, sir.
Yeah. Okay.
So thank you, sir. Thank you for your valuable speech, sir. Are there any queries from the participants? Please, if you have any queries, you can unmute yourself and ask the queries.
What about the technical problem? Is only for this system or others also we have the same problem?
Same problem, sir.
I think maybe you just check your system then. Because
Yes, sir.
yesterday
Yes, sir.
I had keynote lecture and yeah, I think. But anyway, beginning actually my home there is a problem like camera problem. But now in my office
Yes,
it's fine. Actually, I think, and also this go-to meeting, I think it is not very popular anyway.
Yes, sir. Yes, sir.
Okay.
So that,
Okay.
yes, sir.
Yeah. Anyway,
That,
I sent the presentation.
okay,
If you
sir.
want,
Yes,
you can share with the participants. No issue. Okay.
yes, sir.
Yes.
Yes, sir.
Okay.
Yes. So thank you, sir. Thank you very much, sir. All the participants, the next session will be starting in 10 minutes. So please, you can join in the 10 minutes. So thank you, sir. Thank you very much, sir.
Okay.
వస్తుంది సార్ నెట్ అయితే వస్తుంది కరుణ్ సార్ సునీల్
Hello.
కరుణ్ సార్ ఈజ్ ఇట్ ఆడిబుల్ సార్
Yes, ma'am.
ఓకే సార్ థ్యాంక్ యూ సార్ ఓకే
యాడ్ చేసినారు కదా పెట్టేసే దాంట్లో హౌ ఫర్ సెషన్ గుడ్
Okay. So, who is the organizer?
Sir, good morning, sir.
Yeah, good morning. May I know your name?
Sir, I'm Tarun, sir. Tarun Tej, Assistant Professor,
Okay.
SRIT, sir.
Okay, nice. Very nice. Okay.
Sir. So it's a, sir.
Are you able
Yes,
to
sir.
see the screen?
Yes, sir. It's visible, sir.
Okay, right. That's right.
So thank you for your attending this session, sir. Just a minute, sir. Our colleague
Okay,
will
okay.
start with the proceedings, sir.
Okay, no problem.
Shantala ma'am.
Hello. Sir, Tarun sir, is it audible, sir? Tarun sir? Tarun sir?
Yes, ma'am. You can continue, ma'am.
Okay, sir. Good morning, one
Yes,
and all.
ma'am. You can continue, ma'am.
Hello.
Sir, good morning to one and all present here. It's my privilege to introduce Dr. D. Ramasheshu Garu, Professor of Civil Engineering, National Institute of Technology, Warangal, for the 1-week online STP program on seismic analysis of multi-stored building as per Indian Standard course sponsored by AICT. Professor Ramasheshu Garu has joined NIT Warangal in 1990 after working for 3 years in KITES Warangal. He has more than 30 years of teaching and research experience. He taught several courses at BTech and MTech levels with good practical of sharing latest practical information. Professor Ramasheshu Garu has guided more than 80 PV disintegration works and supervised 4 PhDs in the field of structural engineering. He has more than 1,000 research publications to his credit in international and national journals. He visited Singapore and Indonesia for presenting many research papers in international conferences. He has been delivering keynote and extension lectures at several organizations, with including ESCI, VMC, INCAD, AP Genco, Usmania University, Jain University, Andhra University, SU University, and other universities. Professor Ramasheshu Garu is an alternate member of Euro-Indian Standard CED 2.2 Concrete Subcommittee representing NIT Warangal. State Resource Person for Capacity Building of Engineers for the EQ Residence Division. Fellow of Institutions of Engineers India and member of Indian Concrete Institute of IST. He is a review for ASCE materials and register for PhD thesis. Member of BOS and Research Advisory Board of several universities. Apart from teaching and research, he also carried for deliberate the other responsibilities such as head of the civil engineering, head structures division, faculty in charge of G+9 halls of residency, ultra mega hostels, professor in charge of project engineer unit, warden of REC hostels, treasurers and teachers welfare association of NIT Warangal. It's a great pleasure to have here, sir. Thank
Okay, Mr. Tarun.
Sir, yes, sir.
Can I start now?
Yes, sir. You can start, sir. You can start, sir.
Okay. So my screen is visible.
Yes, sir. It's visible, sir.
Right. Nice. Okay. So very good morning to you all. First of all, let me thank the SRIT for giving me an opportunity to share my thoughts and views on certain clauses of the IS 1893, that is the code of practice for the earthquake resistant design. Okay, so today I'm going to compare the 2016 version of the code with the 2002 version of the code of the IS 1893. Okay, in this presentation, apart from this comparison, I will also talk about a few aspects of the earthquake and also certain measures which will help us in reducing the seismic demand on the structures. So some topics may be repetitive for you because other presenters might have already presented this thing. Okay, but kindly bear with me for the completeness of the presentation. I am going to talk brief things about the earthquakes and also seismic demand, reducing the seismic demand on the structure. Okay, so my presentation goes like this. Earthquakes, briefly, I'll discuss about causes and effects of these earthquakes and how to measure the seismic intensity, seismic magnitudes, etc. And followed by the discussion on the changes in the IS 1893 code clauses, and followed by the concepts of design, what are the measures that can be taken to reduce the seismic demand. These are the topics that I'm going to cover within the specified time. Okay. Now let us see the earthquakes. They are the nature's greatest hazard, and apart from this, they are the least understood. And when it is compared to the other hazards, the earthquakes are least understood. And another aspect, unique aspect of this thing is a totally unexpected one, and totally unexpected. And also they cause the instantaneous devastation. So because of these characteristics, the earthquakes creates a unique psychological impact on the people. Okay, why this is unique? You can further extend this uniqueness of this earthquakes is the hazard to the life is associated almost entirely with the man-made structures. Suppose if you are in an open ground, even if earthquake comes, nothing will happen to you. But if you are in a same situation, if you are in a building or a constructed by the human, then that is a dangerous to the inhabitants of the structure. So that is why I say that hazard to the life is almost associated with entirely with the man-made structures, except for the earthquake-triggered landslides. Now you can say whether the prediction can eliminate this hazard. No. Even if a successful prediction of earthquake is made, it cannot eliminate the earthquake hazard. Why? Because suppose you are able to make the prediction of the earthquake, let us say, for a particular area, you'll say that such and such time the earthquake is likely to come. Okay, the people can be evacuated safely, but what about the structures which largely determine the standard of living get destroyed, leading to the great loss to the regional economy? So that is why even if a successful prediction, that's why I say that a successful prediction cannot eliminate the earthquake hazard. Okay. Now coming to the devastating effects of the forces of nature, because earthquakes is also one of the forces of the nature. As for the Hindu mythology, we use the term called Panchabhutas. That is the cause of the natural disasters. We have got, there are 5 elements of the nature. These 5 elements of the nature are Prithvi, Jal, Agni, Vayu, and Akash. Each has got its devastating effect. Each has got a devastating effect. For example, Prithvi, you see the earthquakes, landslides, etc. Then Jal, tsunamis, floods. Agni, it causes the fire, volcanic eruption, etc. And Vayu, cyclones, hurricanes. And in Akash, it's lightning effects. They are very, very destroying, devastating effects on the structures, lightning effects. So all these disasters will have a profound environmental effects and human loss, and frequently incurs the financial loss of the structures. Okay. Now, when it comes to the earthquakes, if you put a question of what are these earthquakes is, the answer is the shaking and trembling caused by the sudden release of the energy, Normally, this is associated with the faulting or the breaking of the rocks in the crust of the earth. So there is a continuous adjustment of the position of these rock masses, which results in the aftershocks, etc. There are different theories behind the origin of the earthquakes. The most popular theories are the one is the elastic rebound theory, another is plate tectonic theory. So in elastic rebound theory, what happens is the rock masses under the action of the loading, etc., they bend until the strength of the rock is exceeded. So whenever the strength exceeds, there will be a rupture that occurs in the rocks. And when after the rupture, these rock masses will quickly try to rebound to their undeformed shape, actually, undeformed shape. So in this process, the huge amount of the energy is released in the form of waves that radiate outward from the fault zones, etc. That creates a kind of earthquake. The another theory says that there is a plate tectonic theory, also called the continental drift. Continental drift, actually. Just a minute. Sir. Hello, sir. Okay. So there is another theory, that is a plate tectonic theory. It says that the Earth's crust is composed of different plates. Actually, these plates are in a continuous motion. So whenever the one plate hits the other plate, there is going to be huge energy release that takes place in the that particular collision point. So that is considered as an earthquake. Most of these earthquakes, almost 80% of these earthquakes occur in the circum-Pacific bolt. That is also called the ring of fire. What is this circum-Pacific bolt? That is surrounds this Pacific Ocean. The Pacific Ocean, this western side of the North America or western side of the South America, and also the eastern side of the Asian part, that is the Japan, etc., etc. And in the American side, it's the California. And similarly on the New Zealand side on the south side, Australia and New Zealand side on the south side. So this is called the circum-Pacific belt. Most of the earthquakes, they occur in this region. Whereas in India, interestingly, this Australian belt, Australian plate, when it collides with the Eurasian plate, then there is that contact is point is lies in the Himalayan region, actually. That's why we feel a lot of earthquakes occurring in that particular region, actually. So this is one theory which says the origin of earthquakes is like this. And certain terminology associated with this earthquakes is the point within the earthquake, earth, where faulting begins is called the focus. That is the creation point. That's the starting point or hypocenter. And the point directly above this focus on the surface is called the epicenter. Okay. So now if you see the statistics of the what is the average number of annual number of earthquakes that occurs. Normally great earthquakes have a magnitude of 8 and higher. They rarely occur. And major earthquakes, yes, the major earthquakes usually between 7 to 7.9 magnitude, they occur frequently. Like that, you can see this particular data. Very minor earthquakes, even in a day, we feel around 8 to 10,000 earthquakes a day. That's very minor, and we don't feel actually that particular earthquake has come or not. Okay. Now coming to the after effects of these earthquakes. Normally the seismic waves that gets generated due to these earthquakes, these seismic waves will travel through the body of the earth, and they reach the surface, and on the surface they travel parallel to on the surface. So normally there are different types of earthquake waves. Primarily they are P waves, that is the primary waves. That is a push and pull is the cause of the motion of these primary waves is due to the push and pull effect, actually. Then the secondary waves will have a side to side motion. Then the low waves, they are side waves in a horizontal plane actually. Then rally waves, they are most devastating earthquake. They are elliptic in vertical plane actually. So these are all the different kinds of earthquake waves that gets generated due to the earthquake. Each wave has got a certain speed. For example, the primary wave has a speed of around 330 meters per second in air and 1450 meters per second in water, and about 5000 meters per second in the rocks. So secondary wave speed is nearly half the speed of the primary wave. Similarly, low wave is has a speed of about 90% of the speed of the S wave or secondary waves. Then Rayleigh waves will have a speed of about 90% of these L waves. Like that, the speed of these waves are very well understood actually. They have got a recorded data of these waves actually. Normally, any earthquake is recorded, effects are recorded in the form of seismographs. Record of these earthquakes are made in a seismograph. So very early seismograph consisting of like this actually. I'll just go to my presentation mode. Okay. So you can see this is the early seismograph wherein you can see the pendulum as well as the recording unit there. So the recording unit and it is subjected, it is attached to the ground itself. Both are attached to the ground, but because of the flexibility of this pendulum, it makes an oscillations during the earthquakes whenever the seismic waves encounter that particular area. So that will make a mark on the recording paper actually. So this is the way the early earthquakes got recorded actually. But nowadays we have got a modern instrument, sophisticated instrument, which can record the acceleration, amplitudes, everything they can record there about the earthquakes. So these are all the some of the typical recorded accelerograms actually. So now, how the earthquakes, how this earthquakes epicenter is located? How this earthquake epicenter is located? Now let us see. If you for this, you just observe one of the recorded earthquake, that is time versus the amplitude of these things. Then you see the first the arrival of the primary waves is indicated by small disturbance on the seismograph, and afterward this disturbance will die down or will come to a point of resting or something like this, or the amplitude reduces. But after some times again this again the whenever the secondary waves will start coming, because secondary waves will have a less speed compared to the pre waves, they arrive at late actually. So again there will be disturbance on the recording seismograph. So like that you can exactly note down what is the difference in the time interval between the arrival of the primary wave and secondary wave. On the seismograph itself, you can know when the primary wave has arrived, when the secondary wave, at what time the secondary wave has arrived, etc. So once you know this difference in the time interval between the secondary wave and the primary wave, then you can go to this particular graph, wherein this graph is the distance traveled by the wave versus the travel time. Distance traveled by the wave versus the travel time. Suppose if you know that, let us say there's around 10 minutes time interval is there between secondary and primary wave, you can take the 10 minutes time interval here and you can draw the horizontal lines at this 10-meter time interval difference. So then you can see wherever these intersect, that is going to give what is the distance of that particular focus point, whether it is 10,000 kilometers or 8,000 kilometers from that recorded station, how much distance the focus point is located, how much distance the focus point is located. So this is the way you can obtain the approximately how much of the distance the focus point of the earthquake is located from the recording station. But now that is not sufficient actually, that's not sufficient. So you have to go for the pinpointing the location. If I say that earthquake has occurred at around 3,000 kilometers from our station, means it can where 3,000 kilometers north or 3,000 kilometers south or to the east or something like that. So how do we locate? So for that, actually, we require about seismograph data of the 3 recorded stations, minimum 3 recorded stations we require actually. Suppose one recording station says that the earthquake has occurred at about 3,000 kilometers from that particular point. Here in this figure, you can see let us say they are the stations located at B, D, etc. So if you draw a circle with the distance of the focus point at recorded at certain point, this is a circle. Let us say one circle. At another seismograph station, that indicates that earthquake has occurred at 2,000 kilometers from that particular point. So taking the 2,000 kilometers as a radius, you can draw another circle like this. So these two circles will intersect at 2 points. But out of these 2 points, which is the focus point, we do not know. So that is why we require the third recording data then to locate the where is the exact location of this particular focus point. So like that, you can pinpoint where is the focus point from a given station. Then how they convert this into the magnitude, how they convert. We hear the magnitude of earthquake is 4, 5, 6, 7 like this. Strictly speaking, how they convert that into magnitude is there are certain calibration charts are there. The calibration charts use the distance in kilometers. This is a one scale, and the extreme right there is an amplitude that is measured at that particular point. For example, if there is a 100 kilometers is a distance at that point, there is an amplitude measurement of 10 millimeters or something like that. You can join this point, this distance point on this scale to the amplitude pointer. Straight away you can join, okay? But that line will intersect somewhere the magnitude scale. So for example, here in this case, blue line has intersected at 100 kilometers distance. There is a amplitude of 10 mm that indicates around 4. But if the same 100 kilometers distance, if there is an amplitude of 20, definitely the magnitude of earthquake is higher. So that is going to give us some idea of the magnitude of the earthquakes, Now let us see when it comes to the earthquake magnitude and its energy equivalence. For example, this energy equivalence, it is energy released from at the time of earthquake, has always been compared with 1 pound of explosive energy that gets released due to the 1 pound of explosive. That is why it is taken as 0 like that. Then if the magnitude increases by 1 number every time, if it comes from 1 to 2, whatever the energy released due to the earthquake magnitude of 2, when it is compared with the earthquake energy released due to the magnitude of 1, it is always 32 times, approximately 32 times the energy will get released. Suppose if I say magnitude of the earthquake released, magnitude of earthquake is 4. If I want to compare this with the magnitude of earthquake 5, the energy released in the magnitude of 5 is almost 32 times the energy that is released at magnitude of 4. So that is a huge amount of the energy for one magnitude increase. This is the kind of energy that gets released in terms of the energy. So now coming to the IS 1893 code of practice. Actually, earlier code of practice, almost way back in 1984, the Indian seismic zoning map consisting of 5 zones actually, zone 1, zone 2, zone 3, and up to 5. Zone 1 is almost, it's like a stable zone, almost Deccan Plateau region. and this Madhya Pradesh region, and there are the stable regions actually. But after over a period of time, when they observed the frequent occurrence of the earthquakes, they revised this particular zoning map. In 2000, they revised, and still that same map is continued even in the 2016. So in this, zone 1 is eliminated. Zone 1 is merged with the zone 2 actually. Because of this, what is happening is before 2000, we have at least some safe zones of from the point of view of earthquake. But when it comes to the 2000, after 2000, there is no place in India which is safe from earthquake, which is considered to be safe from earthquake. That means what I mean to say is you have to consider minimum earthquake forces in the design of the structures as per the code of practice. Okay, so like this, zone 1 to zone 5 is there, but at present it's from zone 2 to zone 5. Now, when it comes to the structures, effects on the structures, mostly the mass and stiffness of the structure, they are going to cause a lot of effect on the earthquake intensities, etc. When this mass and stiffness they are related to the time period of the structure actually by 2 pi under root of m by k. So whenever the mass increases, the time period increases. Whenever the stiffness reduces, then also the time period increases like that. So these are all some of the basic relations between the time period, mass, and stiffness. Of course, all of you, this point is known to you. Why I have taken this point is normally we try to, if we see the spectral acceleration, the response spectrum, you can see, which is given in the IS code of practice, that looks something like this. So you can see this spectrum is drawn between the period is taken on x-axis and acceleration coefficient SA by G is taken on the y-axis actually. So as this natural period of structure increases, its acceleration demand also reduces. So that is why if you can increase the time period of the building, you can reduce the effects of the earthquakes. How you can reduce the effects of the earthquake from this particular equation? Either you can increase the bigger mass for the same stiffness. For the same stiffness, if you use the bigger mass, it increases the time period of the structure. Or for the same mass, if you decrease the stiffness, also increases the time period. So in both ways, we can increase the time period of the building. Okay. There are several effects of the earthquakes. I think you might have seen such kind of pictures in these earlier presentations. So mostly the soft story is the one which is very detrimental to the building structures. Soft story, that means where the stiffness of one particular floor is less compared to the other floors. Or weak story. Weak story, it refers to the strength of the structure. Strength of one particular floor is less when compared to the strength of the other floors, top floors or bottom floors. Like that, they cause devastating effect. The soft story or the weak story, they cause a devastating effects on the buildings. So similarly, due to earthquakes, the buildings, the foundation gets off. Because of that, building may get destroyed, or columns failure will occur. The bending of these frames will occur. Then if there is a high center of the mass, like this flyovers, wherein the high mass is away from the ground actually. So they are the most vulnerable structures in case of earthquakes. Similarly, falling of the objects, which normally causes injury to the inhabitants. Similarly, the liquefaction of the soils, they are the another effect which is very dangerous to the structures. So these are all the some of the failures or effects due to the earthquakes. So damage due to surface rupture, bridge failures, pipeline failures, and fissures due to liquefaction, staging failures, staging for the tanks. That can be RC tank or steel tanks. Similarly, cantilever portions, they are most vulnerable parts in the buildings. All these things will cause different types of failures, and the most of the things confinement failures. A lack of confinement, there will be a lot of failures in the columns and beams, etc., etc. Okay, so in the backdrop of these failures, we'll discuss what are the codal clauses, particularly with reference to the what are the changes in the codal clauses, earlier code and the now present code of practice. So this figure shows the unreinforced masonry, the most vulnerable unreinforced masonry, because of the shaking of the buildings, there is a crisscross cracking will occur in the masonry, which destroys the masonry and its advantages to the resisting mechanism. That we will see how unreinforced masonry has been taken into the code of practice in the design process. Okay, now let us see a comprehensive study of the various clauses that I am going to present. Particularly the changes part only I am going to present. Okay, not changes part, I am not going to touch that actually. Many clauses of IS 1893-2002 has been revised in the new IS 1893-2016. The revisions in the some of the major clauses which I am going to present now. First revision, first change is with reference to the importance factor of the structure. Importance factor of the structure. For example, if you look at the importance factor that is given in the clause 6.4.2 in IS 1893 part 1 2002, there are two factors for given. One is 1, another is 1.5. So 1.5 was used for the important structures. Important structures means community buildings such as hospitals, schools, monumental structures, and emergency buildings like telephone exchanges, because communication systems have to be intact during the earthquake. Otherwise, if the communication system fails. Similarly, bridges, they are the points of the road network actually. Unless the bridges are intact, we cannot take the supplies or the relief supplies to the earthquake affected regions. So that is why there is an importance factor of 1.5 was used. For the other residential buildings, etc., of course, you can take 1.20, all other buildings, etc. That was there in 2002. But when it comes to the 2016, they have elaborated this particular clause. Elaborated means in between 1 and 1.5, they introduced 1.2 as a new factor, importance factor. When 1.2 factor has to be used, this is to be used for residential or commercial buildings with occupancy more than 200%. This is importance factor is to be used as 1.2 actually. Otherwise, earlier what we are doing is irrespective of this thing, we are using 1.5. That's so unnecessary. They thought, so they slightly reduced this importance factor for some of the buildings only, not for the important structures. So what is the effect of this importance factor? As this importance factor, you can see this horizontal seismic coefficient expression. I hope you know this particular AH. That is Z by 2 multiplied with I by R multiplied with SA by G. Z is a zoning factor, I is importance factor, R is a response reduction factor, and SA by G is spectral acceleration coefficient, SA by G. So in this, from this expression, one can see that as the I increases, the horizontal seismic coefficient is also going to increase. Whenever this AH increases, the base shear will also increase, VB, base shear will increase. So this will lead to the increase the amount of the lateral loads on the structure. and eventually increases the size of the different elements of the structures, etc. Okay, this is the effect of the importance factor whenever there is a change in the importance factor from 1 to 1.2. Now coming to the another change in the code of practice is with reference to the design acceleration spectrum. That is, we call it as a response spectrum. So in the old code, that is IS old code means in this throughout this presentation, whenever I say old code means it is IS 1890 2002. Whenever the new code means it is IS 1890 2016. So in the old code, this spectrum, that is equivalent static method, whatever the spectrum that is we are going to use, it is drawn or given up to 4 seconds of the period, time period actually. Whereas in the new code, the spectrum has been extended further up to 6 seconds. This is the first modification. Okay, first modification is with reference to the time period. Earlier it was only up to 4 seconds, and now it is up to 6 seconds. That is the first change actually. For example, you can see this one in the 1893. You can see this response spectrum. It is up to 4 seconds only. Up to 4 seconds only. Of course, the response spectrum takes into consideration different types of bases. That is the type 1, type 2, type 3. Whether the building structure is located on soft soil, medium soil, rocky type of soil. It's up to that. So, for example, in the old code, whenever the period is less than 0.1 seconds, whenever the time period of structure is less than 0.1 second, you can take the advantage of reduced spectral acceleration. For example, if it is less than 0.1 second, you can say the SCA by G between 1 and 2.5 actually. But this is now eliminated in the new code of practice. In the new code of practice, you can see on the right side, okay, this has been extended up to 6. That is the first change. Second change is earlier we used to use the same response spectrum, spectral acceleration spectrum for both equivalent static method as well as the response spectrum method. But now in the new code, they have given separate response spectra for these two methods. For the equivalent static method, this is the response spectrum that is to be used, wherein up to almost 0.4 seconds, I'm talking of the rocky soils. Okay, you have to consider SCA by G 2.5. Earlier, what is that? Earlier, less than 0.1 seconds, so we could have taken some advantage, but that advantage is now eliminated there. So up to 0.4 seconds minimum, you have to take 2.5. There is no reduction in the SCA by G. But for the spectrum that is to be used for the response spectrum, because wherein we do the model analysis, etc., we try to find out exactly what is the time period. So there you can take the advantage of reduced SCA by G. That is the one thing. Okay. So this is the difference in the response spectrums between the to be used for the equivalent static method as well as the response spectrum method. Then what is the advantage of increasing the time period up to 6 seconds compared to 4 seconds? So what is happening is in earlier code of practice, suppose if I want to construct a building of let us say 250 meter height, let us say, with no infill, etc. Okay, and our IS code was silent actually. For 250 meter height, what should be the response spectra to be used? It was silent actually. But now, with increase in the time period, the more height buildings, more taller buildings, they have brought into the code compliance. So now, for example, here you can see maximum height of the buildings with no infill and with infill comparison. You can see as per the old code of practice, maximum height of the building for up to which the code is compliant is 200 meters only. You may construct more than 200 meters, but our IS code was silent on that actually. But now with infill it was 140 meters. But now in the new code of practice, because of the change in the time period, 6 seconds. We'll see in the next few slides. You can bring the building's height up to 344 meters into the code compliance. Within fill, it was made 210, from 140 to 210 meters it is. So this is what the changes in the response acceleration spectrums, okay, effects of the changes. Now, whatever the response spectrum, whatever I have shown in this, they are the horizontal motions, horizontal movements of the earthquakes effects. But for what happens whenever there is a vertical motion, because most of the cantilevers they experience the vertical motion, and because of the other form of waves like low waves, rally waves, etc., there is going to be vertical motions that occur actually, particularly the bridge piers. So what is the design acceleration spectrum that is to be used for the vertical motion compared to the horizontal motion? Normally, this vertical earthquake shaking shall be considered when the structure is located in seismic zone 4 and 5. Okay. Whenever the structure has a irregularities with respect to the vertical or plan irregularities, you have to consider the vertical earthquake shaking. Similarly, whenever the structure is rested on a soft soil, then also you need to consider the vertical earthquake shaking effect. For bridges, it is compulsory; it has to be considered. Whenever the structure has a long span, then also the vertical earthquake shaking need to be considered apart from the horizontal earthquake motions. Then structure has a large horizontal overhangs or structural members or subsystems. For all these conditions, you have to consider the vertical earthquake shaking. So there was a small study which has been presented by one of the authors in the 14th World Conference on Earthquake Engineering. Okay, due to this vertical component of earthquake, if you consider apart from the horizontal, axial forces will increase by about 30%. Then bending moments at particular locations increases by about 10%. Similarly, shear force increases by 15%. This is for one particular structure. They have carried out certain analysis and they tried to measure what is the increase in the bending moments after considering the vertical component apart from the horizontal earthquake component. Then crack widths are increased by 60%. Okay. So because of all these effects, there is a small change in the IS 1893, the new code of practice. Earlier code of practice, what they have given just a small statement, like this. The for design acceleration spectrum for vertical motions is to be taken as 2/3 of the design horizontal acceleration spectrum. For 2/3 of whatever the AH value you calculate, that is to be taken as A towards A. That was the clause in the old code of practice. That the same clause has been made more elaborate. For example, for buildings governed by IS 1893, it is 2/3. For the liquid retaining tanks, also it is 2/3 only. But for bridges and industrial structures, you have to take 2/3. The factor is same, but instead of 2.5 maximum SCA by G, you have to take actual SCA by G into account. That is, you have to carry out the site specific inspections or surveys and exactly calculate what is the SCA by G of the site specific SCA by G. You have to take it. So that has to be taken into account in the vertical motions actually. Okay. Now another change. Apart from the, we have discussed about the importance factor. We have discussed the response spectrum. We have discussed the shape of the response spectrum. We have discussed, and we have also discussed about the how the vertical motions are to be considered. How much percentage we have to consider when compared to the horizontal earthquake effects. Okay. Now the another change is with reference to the fundamental natural period, time period of the structure. In the earlier code, this was the formula that they have given for the time period without infill. Time period is related to 0.075 h to the power of 0.75 for the RC framed buildings. For a steel framed buildings, it was 0.085 times the h to the power of 0.75. This equation I have used in calculating the 200 meter, 344 meter. For example, if you take the t as 4 seconds, you can calculate the h value from this. For example, if you take the t as 6 seconds, also you can calculate the h value. From that only, you can say that by increasing the time period from 4 to 6 seconds, what is its effect on the height of the buildings? What height of the building can be brought into the code compliance. So this you can use it. Now coming to the new code of practice, the same expressions they retain, but in between 0.075 and 0.085, they introduced one more time period expression, that is 0.080 h to the power of 0.75. And they say that the first expression, that is 0.075, to be used for the RC moment resistant framed buildings, and the last one 0.085 is for the steel moment resistant framed buildings. Then in between you have got RC and steel composite buildings. Okay, the question has come: what should be used in the time period expression for the when there is a composite building? That's why they introduced the in between 0.080. Okay. Similarly, when it comes to the infill effect with infill, because infill normally reduces the time period actually. So with infill effect, the earlier code has given a simple expression that 0.09 h divided by root d. That was a simple expression. It was given in the old code of practice. But in the new code of practice, they have made this clause very elaborate, because they have brought into this structural wall effect into the time period. That's why they consider the cross-sectional area of the structural walls. That's why the expression is not simple 0.09 h divided by root d, but it is given as 0.075 h to the power of 0.75 divided by root of AW. AW is the total effective area of the cross-sectional area of the walls in the first story of the building, because the same wall will be continued throughout the height of the building. That's why they take the cross-sectional area, and any floor you can take it, but they say that first floor only it has to be taken. And you can have several structural walls. One structural wall is located at one place, and another structural wall in the same line of the earthquake force is located at some other place. So you have to take the cumulative area effect of these structural walls. How the cumulative effect has to be taken is given by this expression. AW is the sigma AWI, that is AWI is the structural wall at some location, ith location, multiplied with the 0.2 plus the length of the structural wall divided by the height of the wall square. So this is the way you can consider the cumulative effect of different structural walls located at different locations of the building in the plan of the building. Okay, but however, there is a overriding clause that this is greater than 0.09 h divided by the root d. All these clauses, they are in tune with the Euro code, because Euro code, they have taken all these effects into the code of practice. Similarly, Indian Standard Code also, they have considered the similar effects with respect to the structural walls. This is a very great modification into the code of practice actually. Now coming to the here, I have taken some of the literature findings. What is the infill effects actually, which has been published in the advances in the civil engineering. Natural period of the vibration of the buildings reduced by about 7 to 30% and 15% on an average due to infill wall contribution. Okay, so the efficiency of the infill reduces as the height of the building increases. So that's what you can see in these figures. As this height of the building increases, there were some studies made in this particular reference. present published in the reference. Okay, so it shows that as the height of the building increases, the efficiency of the infill reduces. Then similarly, adding a structural wall substantially decrease the vibration of the period by about 23 to 30%. These are all the reported results in that particular publication. Similarly, this publication reviews certain height period relations. There are different height period, time period relations are there used by different people or different course of practice, etc. That means it indicates there is a still lot of study is required on this in this particular area. What should be the exact value of the height period relationships? It requires an extensive data and extensive study actually. Now coming to the effects of this unreinforced masonry. Previously, unreinforced masonry is a infill actually. With reference to this unreinforced infill walls modeling, the earlier code was silent about the modeling, how you can model these in the presence of these infill walls. Code did not say anything actually in the earlier code of practice. Only they have given one equation, simple equation that infill changes the time period. That's all they have taken. But in the analysis, how it should be taken, they were silent actually. That. But in the new code of practice, they have given a clear-cut procedure how this unreinforced masonry has to be taken into the analysis. So they have introduced the concept of, they have used the concept of equivalent diagonal strut method. Equivalent diagonal strut method. For example, you can see this particular figure. This is a frame actually, and in between there is an infill. Whenever due to the horizontal earthquake effect, whenever this earthquake frame, the concrete frame, the RC frame will side sways, definitely the infill will not allow the frame such an easy way actually to sway towards the sides actually. Why? Because along the diagonal there is going to be compression forces. Along the diagonal there is a compression forces. These compression forces will try to resist the horizontal movement of the frame, horizontal movement or displacement of the frame at a particular floor location. Okay, so this the compression strength of this, that is why this is called as a strut actually. That is why it is a compression member. That's why it's called as strut actually. Okay, that equivalent diagonal strut need to be considered in the analysis. How they are going to consider that equivalent strut is equivalent strut means we need to convert that particular masonry into a structural element like this. For example, this is a frame. Previously, we are neglecting this particular. Now, in the analysis, you can introduce one member which simulates the effects of unreinforced masonry. Simulates the effects of unreinforced masonry actually. Okay. So whenever strut means what should be the width of the strut, what should be the strength of the strut, etc. The code has given a clear guidelines. For example, the modulus of the elasticity of this masonry infill to be taken as 550 times the strength of the masonry, FM. Strength of the masonry in turn depends upon the brick strength as well as the mortar strength. So that is why they have given a clear-cut expressions for the masonry strength expressions, and how this EM and FM are used in finding the width of the strut, Okay, that also they have given a clear-cut expressions for this. These are all the elaborative changes they have made in the new code of practice, and in the new code of practice they have taken the modulus of elasticity of the masonry they have taken, and modulus of the elasticity of the frame material or concrete material. Both have been taken into account in order to arrive at what should be the width of the strut actually, width of the strut. So these are all the things. There are changes in the IS 1893 code of practice. There was a small one publication in Indian Concrete Journal by CVR Murthy of IIT. And this what is the effect of this URM unreinforced masonry infill in the modeling? How it is going to be beneficial for the point of view of concrete material consumption and steel consumption. Okay. They have used they have compared this concrete material and as well as the steel material that is required because of the consideration of the URM infill. They have considered Nepal building code and equivalent braced frame analysis they have considered, and European code also they have considered. So these results indicate that though there is not much change in the concrete quantity, but there is a lot of change in the steel quantities. When you are using equivalent braced frame method, that is a strut is introduced, etc. Definitely the quantities of the steel are going to reduce, which is beneficial to the design point of view. Hence, the new code tries to exploit the benefits of the infill in a rational manner. Instead of just completely neglecting the infill, why not consider the infill and take some advantages because of the presence of the infill? That's what the concept of the code. Okay. These results are published in ICJ 2004, July 2004. Now coming to the another effect, that is a soft story effect. Previously, the code has the soft story clause is like this. The soft story is defined as the story in which lateral stiffness is less than 70% of the story or above, or less than 80% of the average lateral stiffness in the 3 stories above. So that means even if some of the stories above a particular story has got a slightly less stiffness, actually it was accepted in the old code of practice. But in the new code of practice, that is completely eliminated. So a soft story, here the definition they have changed. Soft story definition they changed. The soft story in the new code is defined as the story in which the lateral stiffness is less than that in the story above. That's all. There is no 70% or 80% that advantage. They have not given that advantage. So you should maintain compulsorily the story stiffness either equal to the story just below that. Okay. So that is that means this codal clauses with reference to the soft story in IS 1893-2016 has been made more stringent, more strict actually. So that is why in any case stiffness of the lower story should not be less than that of the upper story, because the earthquake effects, they observed that most of the buildings cause of the failure for the soft story. That is why they have made this particular clause more stringent clause. They have made it. Okay. Now coming to the weak story effect. Weak story, there was some relevance in the 1893-2002 code of practice, wherein the weak story is defined as the story in which the lateral strength is less than 80% of the story above that. That 80 up to 20% change can be accepted in the old code, but in the new code that change has been taken away. That means as per the new code of practice, the weak story is defined as the story in which the lateral strength, that is the cumulative design shear strength of all structural members other than that of the unreinforced URM infill. If it is less than the story above, it should be considered as a weak story. Even at 5% or 1% less also, it should be considered as a weak story only. Whereas in the earlier code, okay, 20%, even if 20% less, okay, doesn't matter. But that is why with respect to the weak stories, the code clauses have been made more stringent. Now coming to the another change, one is the dynamic analysis requirement. This when do we need to go for a complete dynamic analysis instead of the equivalent static analysis? that has been made more stringent here actually. In the earlier code, for regular buildings, when the building is located in, let us say, zone 2 and zone 3, when the building height is greater than 90 meters, then only you have to go for dynamic analysis. In zone 4 and 5, when the height exceeds 40 meters, you have to go for dynamic analysis. This is for regular buildings. For irregular buildings, slightly these values will vary. For example, zone 2 and zone 3, instead of 90 meters, 40 meters is the. So that was the conditions they have given in the old code of practice. But in the new code of practice, equivalent static analysis shall be applicable for all regular buildings of height less than 15 meters, that too in a seismic zone 2 only. Okay, less than 15 meters, that too in a seismic zone 2. And all other buildings wherein height is greater than 15 meters or when they are located in the zones 3, 4, 5, etc., then you have to go for the dynamic analysis only. That means dynamic analysis, with this change, what is happening is 15 meters means it's only, you can say, around the 5-story building. Each story, let us say 3 meters, even if you take a 5-story building, up to that, it's okay. But if the story exceeds more than 5 stories, you have to go for completely dynamic analysis. That's what the code stipulates. And also equivalent static method should be used for regular buildings with approximate natural periods less than 0.4 seconds only. Earlier such clause was not there actually. So with these changes, most of the buildings will come under the dynamic analysis requirement. You cannot just say carry out the equivalent static analysis and say that I have carried out the earthquake analysis. Okay, you have to satisfy these clauses. So that is why this has been made more stringent actually. Now coming to the moments of inertia of the different members of the structural. Clause regarding moment of inertia was not there in the earlier code of practice. They have not said anything. They used to take gross moment of inertia of uncracked section. But in the new code of practice, there is a clear-cut clauses are given what should be the moment of inertia to be considered for the analysis, frame analysis, etc. For example, RC and masonry structures, the moment of inertia should be 0.70 I gross to be taken for columns and 0.35 for the I gross, 0.35 of I gross for the beams to be taken. Why they have given very less moment of inertia for the beams compared to the columns? Because beams below the neutral axis, most of the concrete is cracked concrete, we consider. Because of that, they reduce almost to 35% of the gross moment of inertia only to be taken towards the moment of inertia. Wherein columns, because of the axial load effects, the cracking may be slightly less. So that is why they allowed up to 70% of the I gross. For the steel structures, I equivalent is to be taken as I gross for the beams and columns. So that is why this clause is added only for the point of safety, that to post earthquake effects. Okay. Hence, safety, it is more reasonable to consider the cracked sections properties in the analysis. So with this, the code has become more stringent with respect to the moment of inertia of the members. Now coming to the torsional irregularity, this is where the code has made certain changes. I think torsional irregularity, because of what happens due to the torsional irregularity is there is going to be a twist in the plane actually that occurs because of the torsional irregularity, okay, of the building. Now in the old code of practice, the torsional irregularity was based on the drift consideration, maximum story drift. If it is more than 1.2 times the average story drift at the two ends of the structure, then the torsional irregularity comes into picture. So in the new code of practice, instead of considering the drift as a criteria, they have considered the displacement as a criteria. Displacement drift means the difference in the displacement between the two floors actually. That is called drift actually. But here in the new code of practice, instead of considering the drift, they consider directly the displacements. Okay, that is why the code clauses have become more stringent in case of 2016. In this case, whenever the maximum displacement at one end of the structure, if it is 1.5 times the displacement at other end, minimum displacement end, then it has to be torsional. The building needs to be considered as torsionally irregular. So you can observe like this. Suppose this is the plan of the building. At this point, there is a displacement of delta minimum, let us say. At other end of the building, there is a delta max is the displacement. Whenever this delta max is 1.5 times the delta minimum, this particular floor needs to be considered as a torsionally irregular floor. Earlier it was 1.2 times actually, 1.2 times. So now this up 1.2 times with respect to drift actually, but not with respect to delta max. Okay, you can see in this slide the effects of torsional irregularity. You can see how the building has here you can see this end has displaced little less compared to the other end of the roof structure. You can see other end of the roof, other corner of the roof that is slightly displaced more actually. So this has caused the torsional effects that comes into picture. So these clauses have been changed suitably to take this torsional irregularity into effect. Another change is with respect to the re-entrant corners. Another change is with respect to the re-entrant corner. So earlier code, when to consider re-entrant corner, because re-entrant corner there is going to be stress concentrations will be there actually, that they are the regions where the cracks will emanate or start from those re-entrant corners. So that needs to be considered when we need to consider this re-entrant corner in the earlier code, when this length of the offset to the total side length ratio, if it is in between 0.15 and 0.20, okay, we have to consider that. But in the new code of practice, up to 0.15 only they allowed. They have dispensed with that 0.20 actually. So with this, what is happening is the buildings with re-entrant corners, more number of buildings will come into this dynamic analysis or the seismic code requirements. So this is the change with respect to the re-entrant corners. That means that range has been now eliminated. Earlier range was A by L can be between 0.15 to 0.20. But now this is A by L of 0.15 in any direction. In this case, both directions, if it A by L is in between so and so, then we need to consider greater than that, then only we need to consider. But in the new code, in any direction, if it occurs that A by L ratio is greater than 0.15, then we need to consider the re-entrant corners into the analysis purview. Okay. This is the effect of the re-entrant corner. That's why whenever there is a re-entrant corner, you have to strengthen that particular re-entrant corner by providing additional reinforcement, etc. Now coming to the another change in the, I'll take another 5 minutes of time. Okay, diaphragm effects. When diaphragm is that is slab, roof slabs or floor slabs, they are considered as a diaphragms actually. Okay, so as far as the 2002 code of practice, the code was silent with regard to the whether the diaphragm is a flexible or rigid, whether the diaphragm need to be considered as a flexible or rigid. From that for that particular question, the code was silent in the earlier code of practice. But in the new code of practice, they have given certain clauses regarding the consideration, when to consider the diaphragm as a flexible, when to consider the diaphragm as a rigid diaphragm. Okay. For example, if this is the diaphragm, for that particular diaphragm, the experiencing delta 1 is a displacement at one end, let us say. And if it is experiencing delta 2 at the other end. So if you join these two, this is a chord actually. So you can find out average, okay? At any point you can average. But if the displacement at the middle, if it is, let us say delta middle, if the delta middle is greater than 1.2 times the delta average at that particular point, then the diaphragm need to be considered as flexible diaphragm. Flexible diaphragm only it has to be considered. Otherwise, you can consider the diaphragm as a rigid diaphragm. The rigid diaphragm makes the analysis little simple, but flexible diaphragm makes the analysis little complicated. Okay, so this is the way the diaphragm effects have been brought into the code of practice in the 2016 version. Okay, similarly, diaphragm discontinuity. Diaphragm discontinuity, let us see, that is excessive cutouts. Normally, for taking the lifts or whatever it may be, you will make some cutouts in the diaphragms. Okay, so the old code, flexible or rigid diaphragm words are not mentioned actually. But there was a small this thing, whenever this cutout area is more than 50% of the total area of the diaphragm, it is to be mentioned as a discontinuous diaphragm. That's what given in the old code of practice, that's all. But here they have made slightly more elaborative. Whenever this cutout area, if it is more than 50% of total area, it is to be considered a flexible diaphragm. Whenever if it is less than 0.50% of the total area, it is to be considered a rigid diaphragm. So that is the way they have considered the diaphragm discontinuity effect has been brought into the code of practice. That means they have considered the opening effects in the diaphragms in the new code of practice. Okay. Then coming to the mass irregularity point of view, as per the old code, the mass irregularity is considered to exist whenever the seismic weight of any floor is more than 200% of that floor below or above. Then only we consider that as a mass irregularity. Suppose a particular floor is left open and the above floor you have constructed the walls, etc., and below floor also you have constructed the walls, but one floor is left open. So you can see the mass comparison between these two floors. If it is more than 200%, then only you consider that as a mass irregularity. But in the new code of practice, that 200% has been reduced to 150%. So with this, what is happening is the code has become more stringent from the point of view of mass irregularity. Whenever there is a mass irregularity, there is going to be side sway of this particular building, or the twisting about the center of rigidity and center of rotation, etc., of the building response. Okay. Now coming to the mass irregularity effects are most devastating effects actually. You can see in these buildings there is a twisting that occurs whenever there is a mass irregularity exists in a building, particular building. Under the horizontal motions, whenever the mass is distributed irregularly, then there is unnecessary, the building is subjected to twisting effects. Twisting, instead of having a simple side movements, the building undergoes the twisting effects because of this mass. So you can experience this, you can refer to the earthquake tips published by the NICE IITK. You can see how beautifully they explain the effects of the mass. That means they have shown a swing like this. Suppose if you sit at the middle of the swing, okay, you swing in a proper way. But at the same time, if you sit at the side of at one corner of the swing table, then the swing will not be proper actually. The swing will motion will be in a different direction. Okay, so that is the way they have explained beautifully in this particular tips. Everybody need to study those aspects. There are about 32 earthquake tips are given, and then they are free downloadable actually. You can go through those tips. Okay. Now coming to the vertical geometric irregularity. Vertical geometric irregularity. As per the old code, the vertical geometric irregularity shall be considered to exist when the horizontal dimension of the lateral force resisting system in any story is more than 150% of the story below or above. That was the code of practice. Okay, so this 150% has been now reduced to 125% only. 125. That means whenever this the geometry from the point of geometric dimension A, if that A is 25% of the side base width, then you have to consider that as a mass vertical geometric irregularity you have to consider. Okay, otherwise you can consider that as a geometrically non-irregular. Okay, now see, that is why because of this reduction of this percentage 150 to 125, and most of the buildings they come into the vertical geometric irregularity. So why I have shown here small temple picture I have shown here. Okay, these temples, you know that these temples they are constructed, temple gopurams, they are constructed in their size lateral dimension slowly reduces as you go to the top of it. Okay, that reduction also has to be uniform. There should not be more than 125% of the reduction in the suddenly. Okay, so that causes irregularity, vertical irregularity. Okay, now coming to the another change in the code of practice is with respect to the damping value, damping ratio. Actually in the earlier code, damping of 2% was allowed for two steel structures and 5% was there for the concrete structures. But now in the new code of practice, irrespective of the material of the construction, whether it is steel or RC or masonry, the damping percentage has been changed. It's been taken as 5%, common 5% uniform they have taken actually. Similarly, in the earlier code, there was some table number 3, that gives the multiplying factors for other damping ratios, like 2%, 7%, what should be the factor that needs to be considered. That table has been eliminated in the new code of practice. Okay, so with this change, the uniform damping need to be considered for the irrespective of the structures, because normally damping has an effect on the accelerations, SCA by G, and in turn it has got an effect on the base shear also. Because of the increase in damping, the base shear reduces actually. Okay. Now coming to the another clause, center of mass and center of stiffness, the definitions have been changed. For example, the center of mass, it is the resultant of the all masses of the system. But in the new code of practice, instead of writing resultant of the mass, they have written resultant of the inertia force. Because the earthquake point of view, inertia force is the one which has got a major influence. Okay. Okay, the inertial force is maybe related to the mass of the building, but they have changed this kind of, they used the correct words, that is resultant of the inertia force, that is with respect to center of mass. With respect to center of resistance, resultant of the restoring forces has been given in the old code of practice, but here resultant of the inertial resistance acts. That is the way they changed the definition of these terminology they've changed. Okay. Then coming to the increase in permissible stresses, this is very important. In the earlier code of practice, whenever there is an earthquake forces, when we are doing the permissible stress method design, we used to take 33% increase in the stresses. But that 33%, the clause of old code has been removed. The 33% increase in the stresses have been removed actually. Okay. With this, what is happening is because you cannot take the 33% increase, so you cannot take the advantage of the permissible stress method actually. Okay, so what the code intention is, you must use the limit state method. You must use the limit state. In the limit state method, we don't take that 33% increase in the stresses. So the code intends to design the structures by following the limit state method because of the removal of this particular advantage. Okay. Then another clause, I just close it. Increase in the soil safe bearing capacity. Okay. From the soil safe bearing capacity point of view, the earlier code actually permissible increase in the allowable safe bearing capacity. You used to take a 50% increase for the rock passes whenever the basis of rock hard soil. Whenever in the medium soil, we take the SBC increase of 1.25, that is 25% increase we used to take. But in soft soils also 25% increase of the bearing capacity we used to take in the design. But as per the new code of practice, for soft soils, you cannot take any increase. It has to be taken whatever the safe bearing capacity you get it. Okay, earlier code advantage of taking 25% increase, that is now eliminated. That is now eliminated. That means it has been more stringent, and also the for determining the percentage increase in the net bearing pressure of the soils have been classified into 4 types: A, B, C, D. Type D soil has been introduced into the code of practice. Earlier it was not there. Type D soil is unstable, collapsible, and liquefiable soils. So this requires more site specific study, special treatments to the soil according to the site conditions. Similarly, in addition to introducing the new type of the soil, and also using the suitable ground improvement techniques, that the code has become silent with regard to the type of compaction. Actually, in the old code, compacting was suggested actually, but in the new code they do not say anything. You can adopt according to the engineering considerations, because depending upon the literature that is available. Okay, so these are all the changes in the increased soil safe bearing capacity process. Similarly, there is a small change in the separation between adjacent units, the requirement of gap in the different adjacent units, that also has been changed. Earlier, it was when the floors levels are same, it was taken as R by 2, that is the response induction factor divided by 2 times the sum of the story displacement. We used to take it like that, but that is now made as R times the sum of the story displacement. So this clause, normally this clause is to avoid any damage due to the contact of the two adjacent units. That is called that as a pounding effect. You can see here in this building, the adjacent building staircase is coming and hitting the column of another building, causing a disturbance to the column or damage to the column. So in order to avoid such things, we need to maintain certain gaps between the buildings. So that gap requirement has been made more stringent in the new code of practice. Okay. Now coming to the compound walls, there is a small for compound wall design, in the calculating the horizontal earthquake acceleration coefficient, R value and SA by G were not mentioned clearly in the old code of practice. But now in the new code of practice, they mention that R to be taken as 1, that is the response reduction factor to be taken as 1, and SA by G to be taken as 2.5. That's where the code mentions this. I think at this point I will stop here. Okay, my sharing of presentation. Okay. Now, any questions? Okay, if there are no questions, Okay, who is the organizer?
Sir, this is Tarun, sir.
Yeah, Tarun.
Yes, sir. Yes, sir.
Yeah, any small questions
Sir.
I'll be able to answer. Otherwise, they can also contact me through my mail ID, which is given
Yes,
in the
sir.
website. Okay, you can share that.
Yes, sir.
Okay, now
Definitely, sir.
there
I'll
are
share
no
on.
questions. Yeah, definitely. Thank you very much. If there are no questions, I am leaving. Okay.
Right. Thank you so much, sir. Thank you for the session, sir.
Okay, thank you. Thank
Sir,
you.
someone
one and
is
all. Yeah, tell me.
Anyone? Participants? Are there any queries?
Yeah, all of you, please read the clause by clause with the 2002 Code of Practice and 2016 to have a more understanding. Okay, both codes are easily downloadable, and you can just go clause by clause. Make a note of that.
Yes, sir. So thank you
Okay,
so much, sir.
I'll
Thank
show
you so
you
much.
one small picture. I'll show you at the end.
Yes.
That will clarify the things. Okay, now you can see this one, this picture. What is that? You can understand from this picture. Screen sharing now paused. Why? What is this? Are you able to see this picture?
It's visible, sir. It's visible.
Yeah, it is visible. Right. Very good. Okay. It is self-explanatory figure. What this person is trying to do. Okay. Now I'll show you. I'll go to the next picture. Okay. Here you can see the numbers 1, 2, and 3. 1, 2, and 3. Okay. You can see this one. 1, 2, and 3 actually. What is this 1, 2, and 3 represent? This 1 is indicates the determinate part. I mean determinate. 2 indicates the indeterminate part. For example, if this person is holding, there is no tying at the 2, and there is no this balloon or whatever it may be. In the absence of 2 and 3 protections, if he has got only 1, whenever if he leaves that particular one, he will also fall into that water actually. Okay, that means even if failure at one point is sufficient to cause the failure of the system, entire system, he will drown like other person. Okay, suppose for example, in addition to 1, if the protection by way of 2 is there, that means this is leg is tied actually. Even if by slips he will fall, he will not actually drown actually. He will not, he may fall into this thing on the ground, but he will not fall into this thing, water. But now what is the advantage of this 3? Even if the systems 1 and 2 fails, even if the systems 1 and 2 fails, even if he may fall into the water, but he will not drown. He will not drown actually. So that means this 3 is like ductility in the structures. 3 is like a ductility in the structure, providing ductility in the structure. So if you provide ductility in the structure, even if there is a collapse of, I mean, even if the structural elements are subjected to a lot of forces, extreme conditions of the forces, the ductility will come to the rescue of the structure. So that is what I would like to, that means the intention of the code is building need to have a multiple defense system by way of increasing indeterminacy, by way of increasing ductility, etc. So this is what the code intention actually. Okay, now I think I will stop at this point. Okay, now can I leave the meeting? I am leaving the meeting.
Yes, sir. Thank you so much, sir. Thank you.
Thank you very much. Thank you.
Small. All the participants, please join this next session at 2 o'clock. So thank you so much.